create feedback.
All right. Hello, everyone.
No.
Thanks for coming to the second QuiC seminar. We hope you are enjoying your pizza, and we're really excited. Camryn is going to sort of pick back up, I think, with last week and talk about superconducting qubits and cat states, and so we're really excited for that. Unless there are any announcements or any other comments, I think we're ready to start. So take it away, Camryn.
Hello, I'm Camryn. I was also the one talking last week, so thanks everyone for coming back. And so last week we kind of did a quick overview of superconducting qubit or of quantum computing in general, and then talked very briefly about superconducting qubits. And so today is going to be a continuation of that. So we'll be talking about superconducting qubits, circuit quantum electrodynamics, and then also a specific application of how we can generate photonic cat states. Oh no, okay. Yeah, so here on the left, that's kind of everything I just said, but also just a little bit of bookkeeping. So we have a YouTube channel where all of these talks are uploaded. We also have a Twitter account now where I guess we'll post updates. And then we also have a website to where you can find the slides and more relevant information. So to start, this is kind of an overview of the end of the last seminar. So what is a superconducting qubit? So these are small, like micron scale circuits that are made up of these circuit elements. So you can have inductors, capacitors, resistive elements, and then also Josephson junctions. And really there's many different kinds and families of superconducting qubits made up of different combinations of these elements. But the most important element is the Josephson junction. So you can see here on the top right, there's an LC oscillator, and the energy levels for this circuit are all evenly spaced. And so in an experiment, you can't individually address two of these levels as your qubit. But if we replace the inductor with our Josephson junction, it adds some nonlinearity. And so now you can see the energy spacing between the 0 and the 1 state, or what we would call the ground and the excited state, is different than that of the excited state and the second excited state. So this is great for us. Oh, also, if you have questions at any point during, just go ahead and jump in. Yeah, and so specifically, this was an example of a transmon qubit. If you're interested, this is the Hamiltonian that describes this as a whole, but since we're interested in quantum computing and qubits specifically, we just care about it as a two-level system. So really we can instead just write this much more simple Hamiltonian. And so here you can recognize the sigma Z matrix. So we're considering the qubit, the transmon qubit, as a two-level system. And so this h bar omega is the energy spacing between the ground and the excited state. And this is typically in the gigahertz frequency regime. So we can apply pulses by sending microwave tones. Oh, that might be annoying. Sorry about that. We can apply gates by sending microwave tones into our system. And also because of the anharmonic energy level spacing, these are also really often referred to as artificial atoms. And so now that we have our qubit, great, but how can we actually apply pulses to it and measure its state? So to do so, we're going to rely heavily on some theory that was already developed for the field of quantum optics. And so you can imagine a situation where you have an atom between two mirrors, and you can send light into these mirrors, and this will bounce back and forth between the mirrors or resonate between the mirrors and interact with the atom. So it can be absorbed by the atom and excite the atom into its excited state. And then maybe at a later time, the atom can fall back down to its ground state, emitting light at the same frequency. And this interaction will occur at a rate g. And so this was the field of cavity quantum electrodynamics. But now we can replace our real atoms with artificial atoms and move towards the field of circuit quantum electrodynamics. And so now you can see here, we have a transmon qubit inside of a microwave cavity. And so this microwave cavity is now our resonator. And just so you know, for the rest of this talk, I'll be using the words cavity and resonator interchangeably. Yeah, and so we can rely on the famous James Cummings Hamiltonian that was developed first for quantum optics, and we can use it now for our superconducting qubit. And so this Hamiltonian can be broken down into three parts. The first term that has the sigma z here, you might recognize this from a couple slides ago. This is just the part of the Hamiltonian that describes the qubit. The next term that has omega c, this is the part of the Hamiltonian that describes the resonator. So the resonator has a frequency omega c, and then these are the operators that can act on the cavity. So this one is the raising operator that can add a photon to the cavity, or the lowering operator that can remove a photon from the cavity. And then this last term here in green describes the interaction between these two things. So the first of these terms describes the qubit falling back to its ground state and releasing a photon into the cavity, or the other term here describes the cavity losing a photon and the qubit being excited into its excited state. And this happens at the rate g. This is also described as like the coupling strength g. But other than the fact that we can use the physics from quantum optics to describe this interaction, why would you want to put a qubit inside of a cavity? So we get a couple of things from this. One, this provides a clean electromagnetic environment for the qubit. So this cavity really only supports photons at the frequency omega c. So if they're at some other frequency, these photons will be lost very quickly. And so there isn't going to be any unwanted photons to interfere with the qubit. Second, we can send a tone into the cavity at frequency omega 01, and so this is the qubit frequency. And we can use this to manipulate the state of the qubit without populating the cavity. And then finally, and maybe most importantly, we can use the cavity to read out the state of the qubit. And I'll say a couple more words about that in just a second. But to give you an idea of the energy scales that this happens on, typically, like I said before, transmon qubits have energy scales on the order of gigahertz. Similarly, cavities usually are made to have frequencies on the order of gigahertz, and the coupling strength between these two can vary from 1 to hundreds of megahertz. Okay, so I said that you would find out how we can use the cavity to read out the state of the qubit, and to do this, we're going to go to the dispersive regime of cQED. And so that's the regime where the frequency spacing between the qubit frequency and the cavity frequency, or delta, is much greater than the coupling strength between these two things. And in that regime, you can expand and approximate this last term in the Hamiltonian like this. And so again, like before, I have the purple part is just the qubit, the orange part is just the cavity, and then the green part describes their interaction. And if it's not immediately clear why this is useful, you can rewrite this in the following way. And so here I've grouped the green part, the coupling part, into the part that previously just described the cavity. And so now effectively the cavity has this new dressed frequency. And we say that it's dressed because sigma z will take a value of +1 if the qubit's in its excited state, or it'll take a value of -1 if it's in its ground state. So by reading out a shift in the frequency of the cavity, we can determine what state the qubit was in. Yeah.
Is that a simplification, because they're usually like higher levels as well?
Yeah, this all is ignoring all other higher levels. But actually this kind of generalizes. So you would replace sigma z with some other operator to include, like if you wanted to include the second excited state, you could replace sigma z here with some other operator that would correspond to having like a Q trit, and you would get a different dispersive shift based on which out of the 3 states it's in. So yeah, this part generalizes. The main condition to write this Hamiltonian is that there's a dipole interaction between the qubit and the cavity, and that you're in this dispersive regime, because really you have to do an expansion where G over delta is a small parameter. Yeah. Yeah, there are higher order terms like that that are ignored. This only takes into consideration this form of interaction. Yeah. So this term in green here comes from this term, which only takes into consideration like a one photon process. But I think there are some selection rules that limit what kind of multi-photon processes that can occur anyways, that I'm not super familiar with off the top of my head.
I believe that actually the first term, you can only actually absorb 4 in that one photon at a time. I mean, obviously you can't experimentally tell that, but I think the multi-photon interaction generated quantum effects.
No,
Yeah.
you can have like processes and measure that experience.
Yeah, no, I'm saying, but those are generated by quantum effects. They don't have to show them necessarily.
You can write a Hamiltonian.
You can, but you don't have.
Yeah, just for the purposes of this talk is just kind of trying to give people an intuition for what's going on. So there's a lot of, nitty-gritty details you can get into, but I think for those that aren't as familiar, I think we're just trying to get an intuition for about it. And those that are more familiar with this, take everything with a grain of salt, because you know it.
For the experts, is there a place somebody who's curious on the details could see this? Like for example, this Steve Berman's
Yeah, so the reason these are what are called these terms are obtained via the rotating wave approximation. So these parametric gain and loss terms sigma plus A dagger is exponentially suppressed by the rotating wave approximation. So this Hamiltonian is written down assuming that those fast oscillators are averaged. So if you don't make the rotating wave approximation in the derivation of this, you'll have these gains.
Are there any other questions at this point? Okay, so by grouping terms from the interaction onto the the term that describes the cavity, we can read out the dressed frequency of the cavity and infer the state of the qubit. We could have done this a little differently though, and instead grouped those terms onto the term of the Hamiltonian that describes the qubit. And now you can see that the qubit's transition frequency is dressed by the number of photons actually in the cavity. So this A dagger A here is the number of photons in the cavity. And if you're in a regime 2 where this shift, this G squared over delta, or 2G squared over delta here, is the shift in qubit frequency per cavity photon. And if you're in a regime where this shift is greater than the line width of the qubit, you can actually resolve individual photon number peaks in your qubit spectra. So this is an example of measuring out the frequency of the qubit when the cavity is in something called a coherent state, which we'll talk about in a little bit. So don't worry about if you aren't immediately familiar with that. But when the cavity is in a coherent state, you can see these individual peaks in the qubit spectra that correspond to components with, say, 1 photon in the cavity, 2 photons in the cavity, and so forth, which I think is pretty cool. But yeah. So at this point, are there any other questions? Yeah.
We go back to one slide. So the full numbers wouldn't be discrete, right? When is that? The people find that.
Like why this is in discrete.
Why is it not discrete?
Because here the cavity is in something called a coherent state. And so you can think of a coherent state as a superposition of Fock states. So Fock states are where you have, say, exactly 1 photon in the cavity or exactly 2 photons in the cavity. But here you don't have some exact quantum number for the number of photons in the cavity. So it has to do with the type of state that the cavity's in, and this is reflected in the spectrum of the qubit. Does that make sense? Yeah.
Could I just follow up on that?
Yeah.
Could I ask about how this measurement is carried out?
Yeah, so you would do this measurement by applying a tone. Yeah, so here you would apply a tone at omega c minus g squared over delta, which should be the cavity's frequency when the qubit's in its ground state. And then whether that, based on, you can do it a couple ways, but if you just want to monitor the shift in frequency due to this dispersive interaction, you could monitor the shift in frequency as you send in a tone near the qubit's frequency. And when that's resonant with the qubit, then you will get a shift corresponding to the qubit state. So this is sweeping a tone close to the qubit's frequency. Any other questions here? Okay, so next I want to talk about how we can encode the qubit state in the cavity. But to do that, I kind of want to give a little example talking about quantum error correction, which maybe was a bold choice because I'm not super familiar with quantum error correction, but just stick with me for a minute. So you can imagine a situation where you have one physical qubit and you're trying to do some quantum computations on it, and you're worried it might have undergone a bit flip. So we're only worrying about bit flip errors here. And so you manipulate the state of your qubit, and at the end you read out that it's in its ground state. Well, do you know if it truly should have been in its ground state or if some bit flip occurred and you had an error? You can't tell. So maybe because you're a clever scientist, the way you think you're going to do this is by including a second physical qubit, entangling the two. And so you'll say that whenever it's in both your qubits are in the 1-1 state, that's your logical 1 state. Whenever they're in the 0-0 state, that's your logical 0 state. And if you ever measure your system and find that it's in the 1-0 state, then you know that some errors occurred. There's been a bit flip. But even from this, it's hard to tell where the error occurred, when the error occurred, what your true, so you can only say that an error happened, you don't know how to correct for it. So then to go one step further, you could use a third qubit, entangle all three of them, say that the 1-1-1 state is your logical 1, 0-0-0 is your logical 0. And if you ever measure the qubit in the 1-1-0 state, you know that there's been a bit flip for one of your qubits, but really that should have been the 1-1-1 state. So the answer to your computation is that you get out the 1 state. Well, this is great, but do you see how in order to do error correction, you need to continue to add qubits to your system. So more physical qubits make up one logical qubit. And this is just a very not elegant form of error correction, but just as a quick toy model kind of example. And also say your qubits, even when you had 3 qubits entangled, say they were really, really lossy. Well, you might end up in a situation where at the end of your experiment, you measured the 1-0-0 state, but really there's been 2 bit flips. So you can't kind of outperform bad qubits by just adding more of them to your system. So maybe there's some other way we can try to get around errors that might happen in quantum systems. And one way to do this is by encoding the information from the qubit state into a photonic state inside of the cavity. So if we're going to talk about cavity states, I need to talk about Fock states and coherent state. Yeah.
So I hate to go on because you're replacing this other error correction method.
Yeah.
You can go back one slide. Awesome. I don't understand how you could use this for error correction because once you wouldn't observe 1 in 1 state, 1 in 2 as soon as you observe one of the 1
More
states.
error mitigation,
Okay.
or like going around needing error correction, like having just, sorry to answer it.
Oh, that's okay.
for you. I know what you mean. I thought the same thing. I think it's not so much error correction, that maybe
I guess like if there's a tangle like this, if there'd be an error in 1, that is not also on the other qubit?
That's
Yeah.
what she was saying.
There, yeah, you can have, like, if locally one of the qubits interacted. So like, say you have a 2-qubit system where the qubits are entangled, and then you apply a gate to just one of the qubits, that won't affect the other qubit. If that was the part that you were,
Yeah, so when the error happens, the state like that.
yeah, it would be like 110 or something like that, unless you have, say, correlated errors, where this might be affecting multiple qubits at the same time. But that's kind of another story.
Right, but I do want to say that you could do very simple error correction for single bit flips. You would check the parity of each
Yeah.
of the, are 1 and 2 the same, or 2 and 3 the same, and then based on that, you could diagnose your error and correct it. But as you mentioned, only for
Bit flip errors.
so your qubits can't be that.
Yeah,
It just can't do full error correction, but it can correct this
Some.
particular thing.
yeah.
From the standpoint of like molecular qubit design, how would you try to, get rid of this error before it occurs? Is this something that occurs because your states are actually too close and when you try to get a resonant frequency, you don't actually perfectly excite into that excited state, or is this some other effect?
So I don't know. I'm most familiar just with superconducting qubits. However, it could be from a whole range of things. So it could be because your system, your qubit system, accidentally has some coupling to its environment. And so naturally it will just lose the energy to its environment. But there are kind of other types of errors, like you mentioned. So you could be applying some kind of rotation, like some gate to your qubit, and an error could happen during that. Maybe even that could be affected by noise in the pulses you're applying to it. So yeah, I think there's a whole range of things that can cause errors in your qubit system. And if you're interested in like decoherence and dephasing in superconducting qubits, that's what Joe's going to be talking about next week. So yeah. Are there any other questions at this point? Okay. Yeah, so an alternate approach could be trying to encode the information from your qubit state into the state of the photons in your cavity. And so we need to talk about Fock states and coherent states. These are both types of photonic states in a cavity. And so just like you can write your matrices or your vectors in terms of different bases, you can write these states in terms of different basis states. So the set of Fock states is one type of basis states. So here the quantum number n represents having exactly n photons inside of your cavity. Whereas a coherent state, you have to do a summation over Fock states. And so this is, yeah, it looks more like this, and you have a sum of Fock states. This is more like it's analogous to a classical state. And you can think of, it's characterized by alpha, and the amplitude of alpha has to do with the mean number of photons in your cavity. And because alpha can be complex, the phase of alpha has to do with the phase of the photons in your cavity. Also just in general, and well, I guess for the rest of this talk, when I have a Latin number, right, this is a Latin number in a bra or a ket, that means it's a Fock state. But when I have a Greek letter, it's a coherent state. That makes sense. Okay, cool. Yeah, so now that we know what a coherent state is there any way we could encode the qubit state into a coherent state in the cavity? And so one really easy way you can make a coherent state in a cavity is just by applying a drive to the system. So when you think of your cavity that was 2 mirrors, you could just shine a laser into it. Similarly, with our microwave cavities, you can attach a microwave source to your cavity and send microwave tones into it. But this is just creating some coherent state. This isn't actually encoding the information from the qubit state into this coherent state. So we're going to have to come up with a way to entangle and disentangle the qubit and the cavity. So to do this, there's 2 operators that we're going to have to use. The first of which is called conditional cavity phase shift. And so it looks like this. It's a little confusing, but I think we'll be able to understand what it does by looking at how it would act on either of these states. So you can consider what would happen if we were originally in this state. So here, this means that the cavity was initially in a coherent state represented by alpha, and the qubit was initially in its ground state. And you can see this would just leave the qubit in its ground state and leave the cavity in the coherent state it was in. So when you're initially in this state, nothing will happen. But what would happen if instead you started with the cavity in some coherent state and the qubit in a superposition of the ground and excited state? And sorry, these states are not normalized. But you can expand this like this. And so like we just saw with the first term, nothing would happen. But the second term, the coherent state of the cavity would acquire some phase shift from this part. So your resulting state would look like this after applying this gate. So it would only affect the second part. And this is actually a way we can entangle the state of the qubit and the state of the cavity. And if we look at the special case where the phase shift is pi per number of photons in the cavity, this is a way to entangle the state of the qubit with the parity of the cavity. So that's the phase of the cavity if it has a plus or minus phase. So that's the operation we're going to use for entangling the cavity and the qubit, but now how will we later disentangle the two? And for that, we're going to use this operator, which is a qubit rotation conditioned on a cavity's Fox state, which sounds kind of like a mess. But again, I think we'll be able to understand what this does if we consider how it acts on this state here. So the first part, and say we'll pick specifically. So here, M is the is a Fox state that we choose. So when the cavity is in the mth Fox state, the rotation will be applied to the qubit. And when the cavity is in any other state, the qubit will be left as is. So here, if we look at the specific case where we pick m is equal to 0, and the rotation we want to do is pi radians around the x-axis or the y-axis of the block sphere, then we can consider what would happen to this state. And so because this here, the cavity is in some coherent state that presumably has a large mean photon number, and so it has a very small component with the zero part of the Fox state. So nothing will happen to this component when we act on it with this operator. But when we act on it, or when we act on this part of the state, here, because we're in the right Fox state, the qubit state will be rotated by pi, and it'll rotate us into the ground state, which looks like this. And actually, what's important about this is now we're in a separable state. So we've disentangled the cavity and the qubit with this operator. Do these make sense? Or yeah.
Sorry, I'm really interested in the experimental side of it. I was just wondering, how do you do this?
Yeah.
How do you actually control the rotation?
So this is where it's important that you're in the strong dispersive regime, which I kind of brought up at the beginning. And so if you apply, so whenever you manipulate the state of the qubit, you send in some microwave tone at the frequency of the qubit. And so you would need to send in a tone that's resonant with the qubit when there's 0 photons in the cavity, and that would manipulate the state in this way. Does that make sense? Does anyone else have any questions? Okay. Okay, so those were our two really important operations. But in order to actually transfer information from the qubit state onto a state in the cavity, we have to combine this with some other pulses. So you can imagine the following pulse sequence. So initially, say we have no photons in the cavity and the qubit's in its ground state. then we can apply this pulse here in red that will rotate the qubit into an arbitrary state. But here we will choose for it to be in superposition of the ground and excited state. And then following this, again, we can apply a tone into the cavity that will send the cavity into a coherent state. And so these were both just operations that act on the individual qubit or the individual cavity. But then there's our first conditional operation. So this was the phase shift of the cavity conditioned on the state of the qubit. And so this will put us into this superposition state. And then following this, we can send in a tone to address the cavity that will move us from beta to 2 beta and from minus beta to 0. And then we can apply our disentangling operator. So we will go from 2 beta, or sorry, from this state here. So it'll rotate this part of our previous state. It'll rotate the qubit into its ground state. And so now we have a disentangled state. And we can finish this off with one last pulse to shift the state of the cavity. And this final state, this is our cavity cat state, which is a superposition of a coherent state at plus and minus alpha or beta. Does anybody have any questions about this part? Okay, yeah.
But you said shifting arbitrary qubit state. Are you showing how this works for?
I'm showing how this works, yeah, specifically, yeah.
Okay, cool.
Yeah.
Just make sure I-
So you could have started with some other qubit state here, and you would have finished with a different state in the cavity. But that's the important part, that you can kind of map an arbitrary qubit state into some cavity state in a reliable way.
Would one get mapped to beta minus beta?
Yes,
Something like
if you started in the ground state minus the excited state.
Gotcha.
Yeah.
Okay, thank you.
Is this how you prep your ground state before you started? Like,
So I don't know how photonic qubits work, and if there are like manipulations that you would do on a photonic state like this. Like if now the cavity state becomes your qubit and you can continue to do like operations on this state. I was more so under the impression that it was once you have your qubit, you have your qubit, you've done some computations on it, and you want to hold on to that information for some amount of time, you will transfer it from a qubit state to a photonic state.
There are multiple approaches to that.
Okay. Okay, so now that we have our cat state, which was our goal, how can we actually measure this? And to do this, we need to do something called Wigner tomography. And so here, these are just two plots I made with Q-tip to give an example of what Wigner tomography is. So here, this is the imaginary part of alpha, where alpha was the parameter for a coherent state, and the real part of alpha, again, same alpha. And so this is an example of what the vacuum state would look like if you did Wigner tomography. And so it's really a quasi probability that you would find the cavity in this state. And so you can see that it's centered at 0, 0. And it's not just a point at 0, 0 because of the uncertainty principle. It needs to have some distribution, exactly. And so if you want to know what a coherent state looks like, when you do Wigner tomography, it would look like this here, where it's offset from 0, 0 to plus alpha in some direction. And then if you had some other phase to alpha, that would correspond to a rotation about 0. Yeah.
So there's Q-tip has this bug where your center plot, because you said alpha is 2, is centered, it's actually centered at 2, but Q-tip does this weird scaling thing.
Oh, that's in that direction. Oh,
so it's like it is centered at 2, but the way it plots is weird. So
okay.
you can read off the magnitude of the coherent state basically as the coordinate of the center of mass. Probably.
Okay.
It has this, I don't know how it hasn't.
Yeah, I might have also additionally recorrected this in a wrong way. I thought I accounted for this. I did not. I misinterpreted that. So for some alpha, this is a coherent state. Okay, so now what would Wigner tomography on our cat state look like? And so just to remind you, I put the cat state we got on top here. And you can see that there's 2 probability amplitudes offset to each side. And so these are the components of plus and minus beta. But you would still get these 2 probability amplitudes here, even if you just had some incoherent mixture of plus and minus beta. But because this is a coherent superposition, you also get these interference fringes going through the center. And this is kind of indicative of having generated a cat state. Okay.
What do you mean exactly by if you had some incoherent mixture versus a?
Yeah. So do you know what like a pure state is?
Your plot state or?
So say you had your qubit and you put it into the plus X state. So that's like that's like this state, right? And so half the time you're going to measure the ground state and half the time you're going to measure the excited state. Now say you have a lossy qubit where maybe it was supposed to be in the excited state, but it's losing information at some rate. So you have it just in this state, but really you don't measure it in that state all the time. So the first one is an example of a pure state. You can think of it as being on the surface of the Bloch sphere, if you remember like the Bloch sphere representation of a qubit. And when it's no longer a pure state, it becomes some incoherent or mixed state. And you could also schematically think about it as like the length of that vector decreasing towards the center. Yeah.
Okay. I see.
I don't know if anyone else maybe has like a better, easily accessible definition. Yeah.
I'm wrestling with this definition for most, but I'm pretty sure I tried that it's so you have like quantum mechanical probability, where it could be in like a superposition of 2 states, and there's like a 50-50 chance of measurement. But there's also like classical probability. So you might have, you know, oh, I think that Alice prepared this in the 0 state, or there's a 50% chance you put it in the 1 state. And so mixed state or a pure state would be an actual, you could write it as a state vector. And then a mixed state would be something that's, you can't do that to be read as a matrix, where there's both the actual quantum mechanical probability and there's the classical probability of being different things. So in this case, I think like the decoherence would be kind of taken away from that pure state.
Yeah.
Because we don't know exactly how the decoherence is happening. We don't know how it influences the state vector. Does that make sense?
Just to add to that even further, an incoherent mixture is just a mixture that we all think about when we think of a mixture of socks in a drawer. We just don't know which sock. This is classical probability.
Yeah, so it's just sort of random rather than following.
It's just random rather than quantum. Yeah. Or the example of the lossy qubit, that you could represent that like, oh, with some probability, actually the state is the ground state. It's not that you're in a superposition of excited ground state. It's just it's one or the other. You just don't know one.
Gotcha. Yeah, so it doesn't necessarily transform relative to the operations.
It would transform differently than it would transform like a density operator.
Yeah. Okay. Thank you.
Yeah, so these interference fringes in the middle are indicative that you are in a cat state, an actual pure state, and not just some incoherent mixture. And another thing that you might notice with the tomography of this state is that the blue on the plot on the right corresponds to negative probabilities. And so because you have negative probabilities, you know this is a very quantum mechanical state. Yeah, so this was all what I had prepared for today. In conclusion, we learned about how you can manipulate the state of a qubit and read out the state of a qubit with cQED. Also, qubits are lossy, which you'll hear more about next time. And so for more options for error correction, we can move towards encoding the qubit state into the cavity state. And if you're interested in reading some more about this, these lecture series are really great. And then on the top left, this is the paper that I was pulling all the plots from and talking about mostly today. But this was from about 10 years ago. So they've actually gone forward and done actual error correction with cat states, which I think is kind of maybe along the lines of what you were asking about. So yeah, they have new publications that have come out since that better describe how you can actually use these for error correction. There any other questions? Yeah.
I think I missed when you find what it is.
Oh, sorry. Yes. So there's two definitions you can find. One of them is that it's a superposition of both like the plus alpha and minus alpha coherent states. Or yeah, so either the plus or minus combination of these. But then also sometimes they will refer to it at this point as the Schrödinger cat state, where you have, again, the plus and minus combination of the alpha states, but it's still entangled with your qubit. Yeah.
I guess then coherence means the coherence means where this because there's
Yes. Yeah, I didn't even realize. Yeah, whoops. Okay. Thanks. Yeah.
But you're right, yeah, the word coherent was the word overloaded.
Yeah.
Yeah.
Okay, well, thank you for coming and hopefully come back next week.
Thanks, everyone. Let's see you next week.